Those earlier problems that we worked were all single node problems. But another class of problems that you see in chapter 3 are what are called multi-node problems, where in this case you've got an 80-pound load hanging from this point at D. You have a cable here, and then you got a separate node here at B, and you got cables up there. And the problem asks you to find the tension in all of these cables. This illustrates several interesting features. One is, remember, we can write two equations of equilibrium. If I start at B, I have three unknowns at B and no knowns, but I can only write two equations. So I can't start at B. But I start at D, to our free body diagram at D, I have a TDE, a TBD, and an AD. And so on this particular free body diagram here, I have two unknowns. I can write two equations. I can solve for those two unknowns. And so now I'm in business. But this is another example of why you need to draw a free body diagram. This overall picture is not solvable as is. But if you isolate D and draw a free body diagram of him, these two, this is a solvable picture. If you sum forces in the y direction, I've got 12/13 of TBD minus 80 is equal to 0. So TBD is 86.7 pounds. Once you get him, you can sum forces in the x direction, and you get TDE minus 5/13 of TBD. And so you get TDE is equal to 33.3 pounds. Once you get these guys from D, now you can go to B. So sequence is important. And for a multi-node problem, you have to know where you can start, and then you have to know how to walk through the problem. And we're going to see this in the next several problems, that's true. But once we analyze this node here, now I can go to B. This TBD I found to be 86.7 tension, so he's pulling on D. Because he's in tension, he's also going to be pulling on B. So I draw him pulling, and we found him to be 86.7. And so then if you look at B, I have just two unknowns, this guy and this guy. But I can write two equations of equilibrium here. So if I sum forces in the vertical direction, I have 4/5 of TAB minus 12/13 of TBD, and I get TAB is equal to 100 pounds. I sum forces in the x direction. I've got, well, that's not correct. Oh, that's not correct. So in the x direction, I've got 3/5 of TAB minus TBC plus 5/13 of 86.7. So TBC, if I bring him to the right-hand side, he's equal to this guy plus this guy. And so 60 plus 5/13, so I'll turn my calculator on. $60, which is 3/5 of 100, plus 5 divided by 13 times 86.7. That's equal to exactly 60. Oh. No. Try that one more time. Okay. So 60 plus, I use parentheses now, 60 plus 5 divided by 13 times 86.7 93.3. Yeah, did they wrong? Because in the x direction, you got this guy, the x component of this guy, and the x component of this guy. Interesting. 93.3 for BC. Okay. But one thing I want to show you about this guy is if you basically look at this overall if you draw an overall free body diagram of this piece here, and so you get BD that looks like this. You have a horizontal guy and a horizontal guy, and then you have the 80 down. And we basically determined that TAB was 100. If you resolve him into x and y components, 4/5 of 100 is 80. And so on this overall free body diagram, we could have gotten this 80 here from the overall free body. Let me do that on a clean sheet of paper. Well, we'll just do it this way. So if you, without ever solving, it's like this, let's say this is an exam problem. And the problem, all the problem I'm asking you for is the tension in AB. Do I have to solve the joint D and get this guy and then this guy, and then solve the joint B and get this guy and this to get there? Is there a shorter way to get this guy? Well, if you draw the overall free body diagram here, 80, horizontal, horizontal, TAB. And so, because this has no y component, this has no y component, the only forces with y components is TAB and 80. And so I can sum forces in the y direction is equal to 0. Using this as my free body diagram, I can take up to be positive. I've got minus 80 from here, plus 4/5 of TAB is equal to 0. And so TAB is equal to 5/4 of 80, which is 100. And you can get that directly from this overall free body diagram without going node by node. And so this is going to blow your mind at this point, but as we continue to go through statics, carefully looking at a problem and mapping out a strategy to work to get the answers that you seek, and thinking about, so what free body diagram can I draw that can give me an answer or give me some insight in terms of how this problem works? Or you can just use it to check your answer. You know, when you get this guy to be a nice round number of 100, you go, does that make sense? Then you draw the overall free body diagram, 4/5 of 100 is 8, that's 80, that's 80. You're going, oh yeah, that does make sense. So having a way of checking your answers is also very valuable. Let's do one more multi-node problem. And so this was a little harder. Here we had the horizontal cable at D. This guy, I've got two cables at two angles at D. And so D is a little harder, B is a little easier. And so just another two-node problem. So if we start at D, this is our free body diagram. We've got TDE at 20 degrees. I have TBD at 30 degrees from vertical. And then I have a weight, which is 60 times 9.81, which is 588.6. I could rotate the coordinate system, but I just chose to use X and Y. Using this is my free body diagram. And so I've got TD cosine 20 minus sine 30, which is 0.5 TBD, is equal to 0 in the X direction. In the vertical direction, I've got TD sine 20 plus the cosine of 30, which is 0.866 TBD, minus 588.6 is equal to 0. Cosine 20 is this guy, minus 0.5, sine 20, 0.866. The right-hand side becomes 0 and positive 588.6. I can solve that using a matrix on my calculator, and I get these two numbers. Once you get these two numbers, then the TBD is 561.7 newtons. If you draw a free body diagram of B, so you have a TAB that's vertical, a TBC that's horizontal, and so the TAB is just equal to the vertical component of this guy, which is TBD cosine 30, which is 0.866, TBD, which is 486.4. TBC is equal to the sine of 30 times this guy, which is 0.5, which is 280.8. So harder node, easier node. To try to take the overall free body diagram of this guy is a little harder because this angle is not horizontal. So it's not as easy as what we did before. You can say that this horizontal guy is equal to the horizontal component of DE. You can get that from it. And so the horizontal component DE is 298.9. So 298.9. And his horizontal component is cosine 20. So times cosine 20, get 280.9. So this guy should be 280.9, should be equal to that horizontal, and you get 280.8, which we got there. So that's an example of what you could do with the overall free body diagram.